So now let's go ahead and look at how we can use the Gibbs-Duhem equation. And you can come up with similar equations for other partial molar quantities, but we're going to focus on the chemical potential. How we can use this if we say know the chemical potential for one component, how we can use that to find it for another. So let's say, and this is not a random example, this is a relevant example. Let's say we know that the chemical potential for component 2 can be given by this equation. It's the chemical potential for a pure substance. So that's what the star means here again. So we used this notation earlier, and we're going to keep using it throughout the rest of this chapter. Plus RT times the natural log of the mole fraction x2. All right, and so this will be true for, x2 can range anywhere from 0 to 1, right? That's sort of the definition of mole fractions. All right, so if we know that this is the chemical potential equation that describes chemical potential of component 2 in our mixture, what is the equation that describes the chemical potential for component 1? Because that's the idea behind the Gibbs-Duhem equation, is that we have this equation here that relates these. All right, so let's go ahead and work through this, and we'll get an interesting result, and very useful result. Okay, so if we solve the Gibbs-Duhem equation, which again is x1 d mu 1 plus x2 d mu 2 equals 0, well, let's go ahead and solve this for mu 1. That's the one we want to find. All right, so we will have to subtract, so I have x2, we're solving for d mu 1. x1 d mu 1 is equal to minus x2 d mu 2, and then we divide by x1. So we can say that d mu 1 is equal to minus x2 over x1 d mu 2. And now we need to come up with an expression for d mu 2. Right, so we can use this equation up here. Right, this equation is what's describing mu 2, so we need to take the differential of that. Okay, so d mu 2 is equal to d of our expression for mu 2, which is mu 2 star, again, the chemical potential of the pure substance, plus RT log x2. All right, now the chemical potential of the pure substance is constant, so that first term just goes to 0, and so we will just have an R and T. We're considering, again, this is a constant temperature and pressure specifically. That's how we derived the Gibbs-Duhem equation in the first place. So that gives us just RT, those are both constants, and then we'll have the differential of the log of x2. Okay, so that we can go ahead and plug that into our expression for the Gibbs-Duhem equation up here. Right, so we can plug this in for d mu 2 and say d mu 1 is equal to minus x2 over x1 times RT d log x2. And we can go ahead and rearrange this a little bit. We'll move the RT out front. We have our x2 over x1 and our negative sign. And then we can rewrite d log x2 is the same thing as, using the chain rule, as dx2 over x2. All right, this is just a property of the derivative of a natural log. Okay, so now we can cancel x2's, and we get minus RT dx2 over x1. Okay, now we have things in terms of x2's, x1's. We'd like to put things all in terms of x1's, right? All in terms of component 1. Well, we know that if we have any change in the mole fraction of x2, it has to be matched by a change in the mole fraction of x1, but the negative of it. And this is because if we add together x1, not times, but plus x2, that has to equal 1, just by definition. We only have a 2-component system here. Okay, and that lets us substitute and put everything in terms of component 1. So that gives us d mu 1 is equal to positive RT, since we're substituting negative dx1. We have a negative sign here, so they're going to turn into a positive value. And now we have dx1 over x1. All right. And so from this point, if we want to get any, so this is, in some sense, we're done, but we'd like to express this in terms of, what is, mu1 equals something, so similar to how we had our mu2 equation earlier. So to do that, we need to integrate, right? We need to integrate both sides since we have differentials on both sides. So the opposite of differentiating is integrating. And what we'll do is we'll start from a value of x1 equal to 1, so from pure x1, and then go to some arbitrary value of x1. And the reason we do this is that we want to, it's going to be similar to this expression here where we have one chemical potential that's of the pure substance, and it's going to be sort of referenced to that. So the left-hand side is pretty straightforward. We'll just get mu1 at our arbitrary x1. I'll just emphasize that by putting this in parentheses, but we'll write this as just mu1, but this is at arbitrary x1 minus mu1 when x1 equals 1, which is mu1 star, mu1 for pure substance. So this is the left-hand side. So this is this integral. If we integrate just d whatever, we just get the difference, right, at the specific values we're integrating. On the right-hand side of the equation, the RT, well, that's just a constant. And we will get, right, the integral of 1 over x is natural log. So we'll get RT log x1 minus RT log of 1. But RT log of 1 is just 0 because natural log of 1 is 0. And so we can rewrite this expression as mu1 and move the mu1 star over to the right-hand side. mu1 star plus RT log x1. And what we see here is we get an equation for this that basically matches, if we come back up here to our original expression for mu2, our chemical potential for component 2 we said was equal to this. mu2 equals mu2 star plus RT log x2. That means that mu1 matches that, right? It has the same functional form as 2. This isn't an accident. This is a consequence of the Gibbs-Duhem equation. Our two components affect each other equally, right? That's one way to think of it. So the two components both follow the same functional form for their chemical potentials. And that is generally true. It's not just true for this specific equation, but we'll see this equation later, but is generally true. The two components of the mixture follow the same functional form for their chemical potentials. And so this shows why the Gibbs-Duhem relation is useful, and why why we went to the trouble of deriving it. Just want to finish writing that down, right? So the two components follow the same functional form, and and this is not a random functional form we chose. This is something that's going to be relevant for these liquid-liquid solutions that we'll be looking at.